In this video, I will be presenting an overview of our ICML paper, Efficient Iterative Amortized Inference for Learning Symmetric and Disentangled Multi-Object Representations. This paper introduces EfficientMORL, an unsupervised object-centric representation learning framework. This framework provides an efficient way to obtain set structured representations that have three important properties related to symmetry and disentanglement, which we will introduce shortly. Our work builds upon a line of recent methods that try to learn a set of distributed representations, or slots, instead of a single distributed representation. The reason why many researchers have become excited about object-centric representations is that they promise stronger generalization by facilitating compositional reasoning. A key assumption is that each data point, in this case images, is generated by a composition of these slots. Much thought has already been dedicated to identifying desirable properties of object-centric representations. We consider three in this work. First, the slots should have internal symmetry to establish a common format for objects to bind to. Second, they should be disentangled such that a single object attribute is controllable by a single latent dimension of one slot. Third, they should be unordered to avoid imposing an unnatural ordering on objects in the scene, which could in turn leak global scene information into the slots. So we asked whether we could build an efficient generative model with these three representation properties encoded as inductive biases. Previously, no such model existed, and it turns out that the answer is yes. So let's dive into how we formulated this probabilistic framework. Since we assume images are rendered as a mixture model of RGB and mask components generated by the set of latent vectors, our goal is to solve the inverse problem of inferring the set for a given image. A variational autoencoder could provide a way to estimate a tractable posterior over this set as a product of k Gaussians. The current state-of-the-art method, iodine, proposes to use iterative amortized inference to directly refine the VAE posterior parameters starting from an uninformed guess. However, iodine is inefficient because they use a refinement neural network that needs to take as input high-dimensional image-shaped inputs and gradients, and use many costly refinement steps at training and test time for it to work. Our key idea is to cast the iterative assignment of pixels to slots as bottom-up inference in a hierarchical variational autoencoder, or HVAE. Each stochastic layer of the HVAE uses transformer-based pixel-to-slot attention to preserve the orderless property of the set. Inference in an HVAE is fast to compute, and the hierarchical prior could be used to achieve disentanglement via KL regularization. To summarize, representations share a common format in that the set contains k object-centric vectors of the same dimensionality. The orderless property is achieved by transformer-like pixel-to-slot attention at each stochastic layer of the bottom-up posterior. Disentanglement is achieved by regularizing the posterior with a hierarchical KL against the prior. Optimizing the elbow directly is challenging, partly because the posterior is highly multimodal and because of the regularization. So our second key idea is to make use of a few steps of iterative amortized inference to refine the posterior of the HVAE. The refinement neural network can then be implemented as a simple recurrent network whose only inputs are the low-dimensional Gaussian posterior parameters and gradients of the loss with respect to these parameters. When using our two-stage inference approach, we see large improvements in stability and training convergence with even just one step. Using only a few refinement steps is important, since decoding the latents to compute the gradient of the loss is the main efficiency bottleneck. Putting everything together, we minimize the sum of the HVAE's negative elbow with a sum of discounted negative elbows from each refinement step. We reduce the number of refinement steps after an early phase of training following a curriculum, which speeds up total training time. To mitigate posterior collapse, we use Gecko and a modified KL term in the refinement loss, which pushes lower layers of the bottom-up posterior to match the top posterior layer. Please see our paper for more details. Beyond various ablation studies that we provide in the paper, Our experiments on the multi-object benchmark analyzed object decomposition performance, disentanglement, and efficiency. Here we show that EfficientMORL is able to achieve comparable foreground ARI scores against slot attention and iodine, as well as against the ordered VAE Monet on all three environments. Notice that the reconstruction of the HVAE in the third row is already almost identical to the refined output in the fourth row. Dropping the stage 2 iterative amortized inference doesn't hurt test decomposition and reconstruction quality while greatly speeding up test time for inference. We found that one refinement step helps achieve the lowest test KL, however. We quantitatively and qualitatively show EfficientMORL infers slots whose latent dimensions show low correlation, redundancy, and activeness. This is in contrast to the key baseline here for this experiment, slot attention, which we recall is a deterministic autoencoder and therefore learns lower quality representations. To benchmark efficiency, we examined forward and backward pass timing, memory consumption, and wall clock training time. Please see the paper for the detailed results. Crucially, due to the two-stage inference and the curriculum that reduces the number of refinement steps, EfficientMORL trains much faster than iodine. To summarize, we introduced EfficientMORL, a multi-object scene representation learning framework. We hope that in the short term, it will help expedite research on this topic due to its efficient design without having to have sacrificed representation quality. We plan to explore extensions to sequential data, as well as other data modalities like point clouds, text, and audio. You can find our implementation at this GitHub link.